Continue. I request Sweta to introduce the speaker to the audience.
Yeah, thank you, sir. I take the privilege to introduce speaker of session 4, Shibashish Ghosh, sir, and he will handle online practice session on topology optimization using Altair Inspire for additive manufacturing. Shibashish Ghosh, sir, is a production engineer graduate and postgraduate in business management. He spent over 15 years in design, development of product system for automobile and heavy earth moving equipment industries. Before joining Altair, he worked for Kirloskar Oil Engines, Tata Motors, and John Deere. Presently, he is working as a senior technical manager, design and manufacturing at Altair. He is helping product creators with optimum and manufacturing defect-free components and systems. In spare time, he works for his blog, mechguru.com. I welcome you, sir, for the hands-on training session. Over to you, sir.
Thank you very much, madam and sir, and thank you all for taking out time in your busy schedule and joining this session and shown interest. I already started getting some requests on some of the problems you faced during this installation and all. So that kind of shows the interest you have. So let me share my screen and let me share. I hope this is where you should share. Yeah.
It's visible. Any videos are there? You can, when you share the screen, you can select that share audio and videos.
Okay, so right now, what are you seeing in my screen? I cannot see a preview.
Is so, sir, you again go back, sir. Stop sharing, sir. I will tell you.
Stop share. Okay.
Again, go to share, sir. Share screen.
Go to share screen. Okay, share screen. Okay.
Then it will come. All you select. All you select, sir. Entire window you select. Okay. And bottom you have at the bottom you see audio and video optimize. Two options are there at the bottom.
Optimize screen share for video clip.
And also left side audio is also there.
Yeah, audio is also
both
there.
You select. Now select the entire screen and share. So audio everything.
Share, correct. Okay.
Now
so can you
now
see
we are
this?
able to see your screen and audio also, video also we are able to see. Is there any audio here, sir, for this video?
No, I don't have any audio at all. Okay. So audio is, I am the audio.
Yeah, please. Go ahead.
So, sure. So thanks very much. And just a word of caution before we go for the next 2 hours or so, is that since this is online session and I am presently working from home as well, in my native place of West Bengal, in a village, but thanks to this technology nowadays, internet is good. But I mean, it can happen that internet can go bad anytime at your end or my end. So if you see any syncage problem or syncing problem, like my word and my video is not syncing, please alert me by chat or something. So let me switch on the chat, I guess, so that I can see the reaction for the people. Okay. So that will help me, or maybe you can just alert me and open up your speaker, and then you can tell. They can open their speaker, right? I mean, they can switch on their speaker, right, sir?
Yeah, if anyone wants to ask question, they'll raise the hand, sir. Then they can unmute. They can unmute and ask.
Okay, great.
But so I request all the audience, please mute yourself until unless you have any difficult. Otherwise, we will be disturbing the session.
Great. Yeah, sure. Thanks. And also there might be some background noise. Many of them could be some birds or some dog or something. So please forgive me for that. Okay. So now without further ado, let's get started. So today's session, or rather this 2-hour session, is essentially for design for additive manufacturing. Of course, there is a tool. Which we will use to assist us in this journey is what is Altair Inspire. However, I believe that you will get a lot more than the tool, although there is a tool, and we'll also see how to learn the tool. We'll learn many more things than tool itself. Now, before going further on design for additive manufacturing, that is DFAM, first let's understand a little bit on detail. I'm sure many of you already are aware that what is the difference between your DFAM and RPT. Now, in 3D printing world, these two terms can sometimes kind of get interchanged with each other, but they are not really the same thing. So in the left hand side, I have shown a few image or two image precisely on DFAM. So that is designed for additive manufacturing, where a antenna mounting bracket of a space satellite being redesigned. The bottom side image is the original design, and the top image on the top left hand side is the redesigned 3D printed image. Right? If some of you don't want to talk, please mute yourself. There are some feedback coming. Yeah. So so that is what is DFAM. And on the right hand side, you see that there is what is called RPT. So there is a component what you see on the middle of your screen, and that has been 3D printed on the right hand side of your screen, right? So the original component and the 3D printed component is entirely different, as you can see, in terms of not shape, but in terms of the material uses. So you could probably now figure out what is the difference. Let me switch off my camera so that I can remove some bandwidth, right? So so now you could probably understand what is the difference here. So in the left hand side, you see the original design and the modified design is entirely different, whereas the materials are same, right? And the application are also same. I mean, it is fitted on the exact place where it has to be fitted. On the other hand side, in the right hand side, you see that although the shape or the design is same, but the material is different. And also oftentimes it is not being fitted on the production environment. So that means the final purpose of the component is not being fulfilled by the 3D printed component. So to summarize, on DFAM, it is for design for additive manufacturing. That means the parts end purpose with after 3D printing is to actually use it for its end application. If it is a car, it will be fitted on the car itself. If it is a satellite, then it will be actually the 3D printed component itself will be fitted and sent to the space or wherever. And the design will be such that your 3D printing design itself will help you to get the maximum benefit of 3D printing. Now 3D printing has its own benefit, as you know. It has many benefits, including, say, complexity is free of cost. So that means you can make as complicated as possible. You can make it very lightweight and so on. On the other hand side, if you see on the RPT, it is actually the replacement of your actual production component for various reasons. I'm not diminishing the benefit of both either side. There are benefits on each of the side, and there are advantage of each of the side, disadvantage of each of the side, right? In RPT, the whole mostly the purpose is not to fit or use that component in the production. It is just to check the form, fit, and visualization before we go for actual production component, which has to be manufactured by some other means. So that is the difference. Now, today's session, we will be mostly concentrate on the first part, that is DFAM. We will not be concentrate on the RPT, because RPT, there is nothing much left in the design. Design has been done for considering some other manufacturing process. It is just the process. You just 3D print it to check the form, fit, and visualization. On the other hand side, if you see on the left hand side, that is DFAM, design for additive manufacturing. Here, design plays a very important role apart from the manufacturing, that is 3D printing process itself. I hope that is clear. In case it is not clear, please do send some chat, your feedback there. Now, as we agreed that we will go for DFAM, let me, before going deep into that subject and doing some hands-on exercise, let me introduce Altair. Since I am from Altair. Altair is a kind of 30 years old company, which is we started with one software product called HyperMesh. Now we have kind of more than hundreds of software products, which are used in various physics simulation. We are there in almost all types of physics and simulation of component, be it structural simulation, be it fluid simulation, CFD simulation, electromagnetic simulation, your manufacturing simulation, manufacturing process simulation, or say your or what else, machine learning and those kind of high performance computation simulation and so on. So all kind of physics simulation what are used we have some simulation software, and that's our business. And we have more than 2,500 engineers and scientists use our product. Sorry, not use our product. They are part of our team who creates this product. And then more than 60,000 users are there, right? Now, coming back to DFAM, let's understand what is DFAM and how it can help redesign a component. To demonstrate this, what I have taken is a landing gear, and I'll take one bracket of the landing gear, which is shown in that sky blue color in this top right hand side image. If you see that there is a sky blue color image on the top right hand side, I mean component in the top right hand side. So that is this one. This component we will be taking for our study. And right now, this component is made up of casting. And what we'll do is we'll see how to convert this or redesign this for additive manufacturing, and we'll see the complete process of DFAM, design for additive manufacturing, and finally we'll see what will happen if we print it and what are the kind of defects that it will have. So now let's go ahead. So what is the process? What is the complete process in such situation? So the first step of such kind of problem to do DFAM is to understand the kind of loads coming on the components in various joints. So if you see, since this is a assembly, it is not a mere single component. You have that loads are quite complicated, right? And that's what you can see over here. There is a MBD study has been done to understand the loads coming on different joints. And then once we understand the load, so that's what is happening over here. So to identify the load, you have to first do a what is called MBD study, that is multi-body dynamics study, right? Where we can set up a mechanism problem and understand how the loads are coming on each of the joints. And there are multiple steps. For example, we'll first go and create the joint. Then we'll go and define maybe spring and actuators. We'll create the contacts where it is going to land. Then we'll probably choose the materials what is required, and then we can define some more. So, but quite easy to set it up. And then finally we'll get the loads coming on each of the joints. The whole idea is to understand what is load coming on each of the joints. So that is the purpose. If your component would have been a single component, you would have not required this MBD setup. You could directly apply the load there, right? So, okay. So now, after you do that, after you get the load, what you have to do is you have to go for what is called optimization. Now, you might be asking why you should do optimization. The reason you have to do optimization is simply because most of the applications where you would like to, or company would like to go for DFAM, that is designed for additive manufacturing, is where the lightweighting is a very critical aspect of it, maybe for various reasons. Now, one could be the as you know, the material cost in 3D printing process, especially for metal, is extremely costly. If you see in a very high level perspective, it is around say 30 to 40 times costly than your regular material. So, for example, if you see a titanium in a titanium stock titanium, and the cost of a titanium powder which is required for say LPBA for laser based printing process, it is 30 times costlier, right? That can be one of the reason. Another reason is the application where it is used. For example, this aircraft, they are extremely sensitive on weight. So if they can save each gram, there is cumulative benefit. So for example, it's not only material saving, it is fuel cost saving, their flying time saving, and so on. Similar is the case for satellites and so many things, right? So that's where optimization or mass optimization plays very important role. And we predominantly, that's why topology optimization, that is one form of this optimization process. goes very hand in hand with our 3D printing or DFAM, and we'll see that training how to do those things. But what I'm trying to show over here is a very high level how we have achieved this. So what we did is this particular bracket, what we considered is we have taken that bracket, and then that bracket you see over here, that is step number 1. We have converted that existing bracket. If you see, that existing bracket is different. Existing bracket has a different shape, that is casted. This is the one that has been converted to what is called design space. Now, what is design space? So design space is essentially the maximum available space of a component to a engineer, which they can go at the extreme, how much maximum of the area they can take to design a component. So that is what is design space, and that's what has been done over here with the red block. What you are seeing, that is a conversion from the existing design to design space. Then next step is you will apply those loads and support, whatever you have came from the your MBD study. You understood the loads coming in each of the joints, and you will apply those loads over here. And third thing what you will do is you will also tell the software that I want to 3D print this component. And the way you tell this through this red arrow, what it telling is that which direction of what is the direction you are going to 3D print in it. So that means how you are going to orient it. So that is what you are telling the software by this arrow. And the shape what it will be created will be based on the direction also, whatever you have suggested. So that's what you are seeing in concept 1. You are specifying a direction which is different or rather opposite than what you are creating in concept 2. If you see that concept 2, your direction of the 3D printing, what you are specifying, is opposite actually, right? And that's why you see that the shape what it is created in concept 1, which is shown in the top left hand side of your screen, is different than the shape what is created for the concept 2, where the direction is opposite. And you see that you got a different kind of shape. So in concept 1, you have a different shape, and concept 2 is a different shape, because while doing optimization, you told the software that I have a different direction for it. And software has created a concept in such a way that for that particular printing direction, you would need a least amount of support. So by considering the support requirement, it gives you shape. So the direction is important to specify in case you are specifying the 3D printing as your manufacturing process. However, this 3D printing as a manufacturing process specification is an optional item. You may also not specify any manufacturing process as well, but it is always better that at least during the final stage you give that constraint as well during optimization. Other options for optimization has been shown in this dialog box, which we will see in detail while we will go to the our practice session. So now the summary of this slide is that so now that you got two shapes. So now this detailed design 1 and detailed design 2 you get, and now let's understand further that what will happen if I take this detailed designs, that concept 1 as well as concept 2, and what will happen if we apply the same loading condition what was being used for this creating this detailed design. So you'll see that you have this it's now validating that design itself to make sure that these things are kind of passing the requirement. So you'll see that in this top left hand side, what is happening is it is doing a FE analysis of that concept what you were created, and what you are understanding is that how much stress or displacement on those things are coming here, right? So you'll see that here we have some hotspot area in the stress and all. And same thing is being happening in the concept 2, where I have other concept. Maybe it is not so clear over here, but this is the concept 2 is other concept, but the same study has been done. So basically structural analysis of that design concept we are taking, and then we are understanding the stress and displacement. Why we are doing so? Because we have to make sure that these designs are going to perform in the field, right? Those are that we are trying to ensure. After that, what we are doing on the right hand side of your screen is actually doing a 3D printing process simulation of that concept. Why we should do that? the reason we are doing this is because we want to understand what is the maximum distortion and the residual stress and the thermal behavior of this component, and we will understand that in doing the simulation of 3D printing process for both of the concept. And all this will help us to choose the right concept, and that's the whole purpose of this workflow, where you start with your existing design. You'll take your extract your load, apply those load, optimize those concepts, and then you re-verify those concepts for structural as well as manufacturing process requirement, right? And that's the complete workflow of um, your design for additive manufacturing with Inspire. So now, what are the tools required for doing this journey, right? I mean, fulfilling this journey. So there are many tools available within this platform, right, from MBD to optimization. So MBD helps you to understand the load and identify the load, to optimization, where it will help you to reduce weight, to doing structural simulation, a tool for doing structural simulation. And then you have process simulation tool, including your 3D printing process simulation, that is Print 3D. And all of these tools are very easy to learn and use. They are fast, they are accurate, and they are affordable. And all of them comes in the same platform, which will anyway is better because you don't have to learn so many things, so many tools to do this complete exercise, right? So in a summary, this tool has quite some powerful feature. We'll see these things in little detail, and maybe these are little more technical, but just to give a high level idea, that it has quite good number of what I could say fine tuning parameters to play with as far as the optimization is concerned, and it also has a good amount of constraints as far as the additive manufacturing is concerned, and that anyway will give you kind of end-to-end platform which is sophisticated enough to fulfill your DFAM journey. Now, that was a high level overview how this DFAM, or the design for additive manufacturing process, works. Now what we'll do is we'll actually take and do some hands-on. And for doing hands-on, I would recommend you to open Inspire tool, which many of you would have already been installed, and also open the instruction manual what I have already shared, right? So please open this, and we'll go step by step. Now, the component what we are going to choose today is a spinal implant, and that will look pretty much kind of similar to what has been shown in this screen, right? Just a confirmation. Am I on the? I mean, everybody is able to see my PDF, or is it the screen is showing still that previous PPT? Can someone please confirm?
We are able to see, sir. We are able to see.
Okay,
Perfect.
thank you very much. Thank you. Okay, now we are going to see how to do DFAM for this spinal implant. To explain a little bit how these things works. I mean, of course, I'm not doctor. I'm sure many doctors are there. So I'm engineer. But what I could understand the load cases. The reason we should know how these things is being used in the field by the doctors is to understand the loads and support condition what is required for 3D printing, our optimization process. Now, this piece of implant is being pushed by this. There is a rod over here which is connected by threads over here in the side, and then that has to be pushed, and then it should fit between two piece of this spine, right? And then that will sit there. And if you see in that, I don't know whether it is clear or not, there is in the middle, there are either hollow or semi hollow. There can be lattice, there can be anything. That is also very important feature because that will allow the growth of the bone, right? So that is what is required. And also this piece of spinal implant, or any implant for that matter, has to be as light as possible, The reason being, it will add additional weight to your body, and of course you don't want carry extra load, and you don't want to load your spine also with some extra piece of heavy metal, right? So that's why it has to be extremely light, as light as possible. But at the same time, during this insertion as well as during this placement and after placement, you don't want it to collapse. So that is another important thing, because if it is collapsed, that means it is failed, and again you have to remove it, and there are a lot of complication. So it has to be strong, it has to be lightweight, it has to be perforated inside, so that bone growth happens, and it also has to have some features which will allow it to push it on the right place, and it also has to have feature on the top which don't have to be very smooth, because then it will not fit, it may slip. So all those things has to be taken care over here. And since each of the component can be size can also be different, because this spines size can be different from person to person, so it should be ideally be customized to a specific person's dimension. Of course there are mass produced components are also there, but since this aspect is very important, so that it fit on perfectly on everybody, so that's why this 3D printing is a better option than mass production. So now what we'll do is we'll open this Inspire software. Please invoke this Altair Inspire software. You have not invoked. If you have not invoked, so please invoke, and you can invoke it from your program files, or you can simply type Inspire here if you have already installed, which is the case I am assuming, and then you open it over here. I already opened it, and once you have opened it, you should see a GUI more or less same. If not same, then you may also see something like this as well. So all are okay. So both things are okay. And in case you don't have anything on the left hand side, please go to your view and click on model browser and property editor. So make these two window appear over here, right? And next step, what we will do is once you are done with this and your setup is like this, we'll go to open this, and then yeah, these things we have already switched on. So we'll press control and O, that is open, and we'll go to that folder, and you open this parasolid file. So this 00 spinal implant, that parasolid file you open. By the way, there can be other type of file also could be used for doing this optimization study and 3D printing process simulation study, which are listed over here, right? But here we have a geometry which is in parasolid, so we are opening that. So you just click open, and it should open, right? You should see a CAD model like this. Now this CAD model has three components, 1, 2, and 3. If you want to see it in a better way, you can also go to view, go here in the file, edit view, go to view, and go to auto color. So what it will do is view auto color. What it will do is it will give you a different color for the different components. So from there you can understand which color is, which component is up to what limit and so on. So after doing this, what you have to do is I have to go back to my PDF, and I'll see. Okay, so now what you have to do is click on the structure one. Click on the okay. So now what you have to do is I have to go to, if you are not in the structure tab, so there are many tabs are there. If you are not in this tab structure, if you are somewhere else, so please click this structure tab. So you should see this kind of icon over here. So these are all the tools which are essential, or which will help you to do this optimization study, right? And once you are there, what you do is you choose this component. So this middle component, this one, that is one, and say right click and say design space. So you see that I have made this as a design space. So right click and make it design space. Make sure this is tick. So you have to go here and you have to tick it. So I'll see that this is design space. So you declare this as a design space. So now the design space is the space where the optimization will happen. So that means it will remove material only from the design space. It will not remove material where there is non-design space, or the area which you have not declared a design space. So for example, this area you have not declared as design space. This part you have not declared as design space. So in that way, it will give flexibility to keep some of the essential areas, right? It will give flexibility to keep some of the essential areas to not remove material from, right? And that is important. And by the way, you can have multiple design space as well. If you think that your geometry is complicated, say you have, say, instead of spinal, you have jaw, where multiple components are there, you can declare multiple component as design space as well. But here we will just choose one component as our design space. Now, next thing is, we'll go back here and probably we'll define the support and load. And then we'll go for material probably, right? So yeah. So what we'll do is, next is you have to tell the software that how this, if you see this thing, not this one. If I go back here, so how this process is going to happen. So that means in the field, which are the areas the load and restriction will come. So that you have to explain to the software. And to the way you have to explain to the software is through what is called these loads. So there is this loads icon available under the structure tab. And from here, you have to select the right tool to declare those, to define those loading condition and restriction condition. So what it will happen is that first load will come here, that there will be some pressure which will be applied between these two pieces of your spline, right? And as a result, what will happen is it will apply load on the top surface. So you have to choose that. So to apply load, you have to go here and select this force. So now one word of caution over here is that there are multiple kind of icons or tools clubbed in many of these toolbars, tools in Inspire to help you save some space actually. However, not all of them are same, will perform the same function. So for example, if you want to apply torque, you have to click here, not here. If you have to apply pressure, you have to click here, not here. If you want to apply support, you have to click here. So each of them has their own function. So you may, in the initial days, you may actually put your mouse there for a couple of seconds and it will show you a small, instruction that what it is going to do, right? And accordingly also you can choose. So here we are going to choose force. So left click on force and it will read the instruction. So saying that select a point, edge, face or hole. We have a face. So we'll choose this face. Make sure that you choose here. So you'll see that your icon will change. So that your icon has changed from here to here. So here, if you see that your cursor in the side of the cursor, your icon is suggesting that this force is going to apply on a plane, right? If I go here, you will see that it is suggesting that it will be applied on the edge and so on. If I go here, it will say that it is going to apply on a point. So make sure your icon shows that it is applying on the plane, not on the edge or point, right? And then left click. So as soon as you left click, you will see that that whole surface will be selected. You put a value of 200 Newton. So you put a value of 200 Newton, right? So that means you will see that in the model browser, which is on the left hand side, your load case 1 will be created and a load of force 1 will be created, which has a value of 200 Newton. Now I not only want load here, I also want load here. So what I'll do is I'll select another force here. I'll select this surface as well. And this time also value is same. So you have two loads. You could have selected in control by pressing control as well, but does not matter. You will put this both the surface separately. So 200 is applying over here and 200 is applying over here. Total 400 is applying. And if you could have pressed control, then you would have to actually add 400 over here if we put control, right? But we want separately 200 applied, 200 Newton applied over here and 200 Newton applied over here. 200 Newton means 20 kg, right? We are applying that. So now to come, you see that as long as you are working on a particular option, that option is glowed. So you'll see that it is glowing. So that means this option is activated. Now to deactivate or come out of this option, you just have to right click anywhere and then there will be green tick. You just have to you just have to come out of that option, and we see that this option is no more glowed. So that means this is done. This options function is done. Now on the top surface, you have already applied load. Now what happens is you have to restrict the bottom surface, then only this load will be applied, right? To do that, what you have to do is you have to go to this support over here. So there is a support, and you have to choose this surface and this surface. So I am now supporting this area. So that means I am restricting that area, resting that area. So I am resting this surface and applying load on the top. So resting bottom and applying load on the top. So that is my first load, first type of load I have applied. So there is a rest in the top, and the top load are coming. These are basically spinal pressure or force coming between the two spinal, spinal sectors, right, where it will sit, right? So that is the first thing. Again, to coming out of the command, you just right click, and then you should be coming out, right? So your support is done and your load is done. So let's see if anybody has any question. So I don't know how to see this. Oh, there is a question. Okay, it seems everybody is fine. So if anybody has any question, please put it in the chat box so that I can
So if
understand.
anyone want to interact now, also you can interact, or you can put in the chat box.
Yes. These things are very easy though, but if you want, you can if you have any doubt or you have not reached up to this point, then please do let us know. I can help you on that. So because the subsequent steps are dependent on it, and your result will also be dependent on it actually. Okay. Anyway, I think it is
No
okay.
questions.
So now next load is, if you observe over here, there is a rod which is connected by thread on this, and which will push this this implant into the gap in between the two spinal pieces, right? I don't know what they call in medically, maybe someone will tell. So there you have to push it, and that will also apply some force, and that will apply over here. So again, we'll go over here, force, and we'll select. Now this time we have to select this cylindrical hole, right? So you'll see that this hole is getting selected. Make sure that is what the case for you as well. So you select this, and this time we'll not choose 200, we'll make 100. So basically we are applying 10 kg. Again, I have done some research, but this may vary, but I am sure you understood if you understand the procedure, you can change or customize as per your requirement as well, right? So now once you have done that, so your load and support setting is done, and more technically in engineering term they call load and boundary condition, so that you have done. So you have one load case that load case itself, you have three forces, this force 1, force 2, and force 3, and you have two supports basically on the bottom side of your implant, right? Now, once you are done with that, next step, what you have to do is you have to define your material, I guess. Let me go ahead and check. Yeah, before that, we have to save it. So press Control S so that your work is saved. So you can press Control S, and give a name. For me, it is already saved, so I am not going to save again. But please save it so that in case something happens, you can start working from here and you don't have to start from the beginning. So give a meaningful name, maybe 01. I have given actually 01 spinal implant, and you can then save it, right? Okay, so after you saved, next step is to define your material. So how to define material? You go here. So here I am assuming that complete all the parts of this component, or the complete component, is made out of say single material. So I will assign single material in all these pieces. However, you can also define different material as well, but I'm sure that will not be the case if you are going to 3D print it. So single material itself will make sense. So for that, there are you just have to click here. So that is your top level of your model browser, and right click, and you say material, and choose titanium as a material. So TI17, you can choose this material. There are many other types of material, and you can create your own material as well if you don't see the material of a choice. Or even if you see the material of your choice, you want to understand what are the properties considered, you can go to this material icon, and then you can go to material library, and you will see that how this material is defined. In case you want to create another material, all you have to go to my material and click this plus button over here, right? And there will be material 7, material 6, this generic name will appear. You double click over here, and then you can you can change these values. You should be able to change this value actually. I don't know. So you can change these values, and you can give a name, give whatever name, maybe titanium 1 or something like that. And then you can also edit these values of Young's modulus, Poisson ratio, density, yield stress, thermal expansion coefficient, then your thermal conductivity, and so on. So all those values you can change and then make your own material as well. So then once you are done, again you can assign those material. If you see your material would also appear over here, you will see that there is this material you have created, and I can assign that material as well. So that is what is material definition. Now once your material is defined, next step is to run the optimization, right? To get the minimalistic or optimum shape or optimum material required. So by now, if I switch on the mass, you will understand the mass of this component. So that is around, say, 5 gram. It is actually very less with titanium. You can further optimize it as well, So now to optimize, how to do that? You have to go to this run. So in the structure itself, you have run this group of icon, and there I'll go to this play button called run optimization. I'll go over here, and here first thing appears is the name. So this name is a different than, can be different than this name by what you have saved the file. This name is the name of the iteration you are doing. So I can simply give one, or I can give some other meaningful name, and that will appear when you will done with the optimization. So give a good name so that you can recognize it later, that what are the option used in the optimization, and accordingly you can see the result. So you can may probably say that I used titanium over here. Then I use certain say percentage of material removal, maybe 30% and so on. And then I would probably say that I have used certain thickness, maybe 1.5 mm thickness and so on. Like that, you can give name. Any name is okay as long as there is no space and all. Then second option is your type of optimization. As I said earlier, Inspire is a quite powerful tool as far as the optimization is concerned, and there are wide variety of optimization supported within Inspire. And out of which topology optimization is one we are talking about, because that is what will be more meaningful for your 3D printing application, that is DFAM. There are other types of optimization as well. For example, topography gauge, combination of topography gauge, lattice, polynerve shape, and also on. If you want to learn more, you can go to help. You can just press F1 and it will. So if I just press F1 over here, it should give me to the help page of this. Anywhere, wherever you stuck, you just press F1 and it will explain what all everything is there and so on. And you can learn more by going to help many things other than what we are talking today, right? So we will choose topology here. And under topology, there are two things. One is objective and then the target. So there are these two things for each type of optimization. So to optimization algorithm to run, these two things are required. One is objective, that means what it has to achieve. And then target, what are the boundaries, it cannot cross. So that is the two things. In the objective, what we are saying is that we want maximize stiffness. And in the target, what we are saying is that we are giving a mass target. So what we are saying over here in the target is that percentage of total design space volume. So what is design space volume? So this is my design space. If this design space is 100, what we are saying is that we want to achieve a design which is 30% of this 100. So that means we want to remove 70% of the volume and want to keep 30%. And that is one way of defining this. And where it should keep 30%, the places where it requires it most based on this loading condition. Based on this loading condition, wherever it requires the material or the material will be most contributing material, there only it will be kept there. Rest area where it is not contributing to this load and support condition, it will remove. And that way it will keep the 30% of the most important material for this given loading condition. Another way of defining your optimization is to defining through mass target, your safety factor target. So you can choose objective function as minimize mass, and you can say that I am not sure about how much percentage of material I want to keep, but what I want to do is I want to achieve a certain minimum factor of safety. So that means no area will go below this factor of safety, right? It will give the shape which will be having factor of safety or minimum factor of safety not less than this one. There can be other option as well, such as frequency target and so on. So we are now, for now, we are doing with maximize stiffness with certain mass target. So we are saying that I want to achieve 70% lighter design space than what is there at present, right? Now you can also combine this target and objective with some other constraint we call. So say as frequency constraint, I can say that apart from this, you also give me the, make sure that my design has certain minimum frequency, you know. Now for medical application, I don't know how much relevant it will be, but for other application, maybe in medical also it will be relevant. For example, if it is a spinal piece of spine, then when a human being is either walking or running, that much vibration it will exert from the leg, right? So that is excitation frequency, and your piece should not have that frequency, right? So that otherwise it will be vibrating too much, right? So but on the other hand side, if you see, for example, a component which is mounting a engine, now engine has certain frequency, say 36 hertz. Now you would as a designer would target your engine mount brackets frequency to be much higher than the 36, right? Normally people do 2 times or like that, so that it never resonate during the course of starting from 0 frequency to that 36 hertz frequency for the engine, right? So that kind of application you can also define, or rather that kind of requirement you can also define over here. But for now we are not doing that because we are not sure about the targets. You can also make it maximize frequency. You say that I don't know how much frequency I want, but I want to make it as high as possible, that frequency. But we are not doing this over here. If you want, you can do it maybe later during your practice. Next is your thickness constraint. What is thickness constraint? So thickness constraint is essentially when it will remove material, it will remove material in kind of places, each places, like some chunks it will remove, and it will create some members. Now those members, you can control the thickness of those members, how much you want, right? So that is what it is telling. And this has other importance is that your mesh which will be created will also be governed by this, by the algorithm in the backend. Although it is not visible in the front end, but it will be used as a mesh size parameter in the backend, right? So here you can keep it auto, but auto may be very, very less for the depending on the size. What we'll do over here is we'll put 1 as our minimum thickness constraint. Make sure your unit is mm. If you see unit other than mm, then you can go in the bottom right hand side of your screen and make it to this value, that is mmks, where unit length is mm, kg, newton and second. And you can also switch on the flag of maximum, which will be by default 2 times the minimum. You can make it higher as well, but you cannot make it lower. So it has to be either 2 times of the minimum or more, right? So that is what you keep it. Now, then there is option called speed and accuracy. You don't have to change anything. There are 2 mode of speed and accuracy. One is called faster, another is called more accurate. For optimization, faster is good enough. Contact, you also keep it as default. Gravity direction, you say no. It will not make any difference in this case because the weight is very less, so you can make it no. Then you have load cases. Now load cases is what? This is one load case, but you depending upon the complexity, say other piece of your body parts, it may have multiple load case as well. So it can have load case 2, 3 and all. and it will list all those load case over here. And you can also choose whether you want to select all the load case or you just use few of those load cases. So like that, you can switch on and switch off as well, and you will say run. So once you are done up to this, you can say run. Please, I'll pause for a few seconds. Please let me know in case someone has any difficulty reaching up to this. Maybe you put your thought. If somebody has any difficulty, put it in a chat. Okay, I saw Mayur said no. Okay, I'll wait for one more second in case someone has, and then I'll continue. Okay, great. So that's fine. In fact, this tool is very easy, and it will be, there might be no problem till this time. Now, all you have to do is, if you have reached up to this and you have given a meaningful name over here, you just hit run button. And you should see this kind of dialog box over here, which is kind of warning, which is telling that you have some load or boundary condition, load or support, which is on the design space, which is technically not a good practice. But you can say, okay, I want to continue. You say continue, so that it will still run, allow you to run. And once you run it, you should see this kind of status. So what it is telling is that it is running. You have name whatever you have given that came, and on top of that, it also added something like what is your objective function and what was your mass target that has been added. So you have given only up to this, and it has added this. And it is now telling the status, how much it has gone. Once it will be complete, you should able to see the result, right? So let's wait till the time this run is complete. It should not take much time because I have run it before, and that's why I kind of customized it a little bit so that it can be solved if everything goes well, of course. My machine is 32 GB machine, so maybe not all of you could be able to solve, but I don't think it will take great amount of time. It should not take actually more than 5 minutes with this setting, to be honest, for maybe maximum 10 minutes for some of you who are having very maybe less hardware on your machine. While this model is running, let me introduce some of the other thing what you might be useful for you. So one thing I have already talked about is the help. Now help can be accessed by pressing F1, or you can also go to file and help. And then there is this help tutorial, download offline help, then you have APIs and all. But this tutorials is quite useful and like crisp. If you don't want to spend very long time to learn this tool, you just go to tutorial, and there are, I think, 7 to 8 tutorials only. And if you do that, you will be actually thorough. Because I have not explained everything over here, which is not possible given the time limit we have, each and every tool and each and every icon, because there are many interesting things about in Inspire which you may like to learn, right? So that you can learn actually through this tutorials. You can also learn them through what is called Altair University. So if I go to Altair University, for those who are not familiar, I mean, I think many of you are actually familiar because you have probably downloaded somehow you got interacted with that to get the license and all, I am sure. So this is the university, and here lot many resources are there, not only for students but also for teachers. And then there are courses and certifications as well, which everything is free of cost actually. Maximum you need is your iCard, and then you can enroll. It is not only with Inspire, you can run many other things. And if you are either student or teacher, this is a great place to enrich your knowledge, not only for the tool, but also there are many things which are domain specific. So please do visit there. You can also enroll yourself with your university industry outreach portal. There is somewhere it has. So you please enroll so that companies, when they hire, they go sometimes here and then pick some of the candidate who they need, right? So that is one place. And then here, if I go to, I think, learning library. So then you should see the all those exercises, all those programs. So if I have to learn, say, course, no, I want to understand, say, self-paced course, and then I'll go to discipline. Okay, so let's say I want to understand. Okay, let's skip this. I will say English, and then we'll go to discipline, that is conceptualization category, that is optimization. You can go here, and then you should see this actually completely. This is a self-paced, course, right? So it's yeah, you can go there, and there are many other places you can go. Now this run, what is going on, if I want to understand what is actually doing in the backend, I can always go to open run folder, right? And what it will see that it will create all those supporting files which will be required in the backend, right? And there are many things and which will be useful. Some of those things will be useful many a times when you want to, especially want to debug, right? And one important file is this error log. So you can go here and check if there is any error. No error, it seems. And you can also go to, so you see that these H3D files are actually result files. So this is what started creating. So that means it has gone to meshing, and it has solving. It has almost kind of end of the solving. And that's why you see those H3D file is getting created, because H3D files are actually the result files. But it may not finished solving yet. So that's why it is still writing those, information over here, right? If I go back again, let's see how much it has done. Right, it is doing those things. Okay, it is taking a little longer than I expected last time. Maybe my resource is a little bit tied up with something else. I was expecting a little less, but anyway, we should see the result here soon. Maybe wait for that result to come. Yeah, it's still writing. Yeah, it's still writing. Okay. I have a solved model as well, but let's see this only. If it don't solve by another 3 minutes, that is 12:30, we'll switch to, I'll show you the solved model and explain it further, right? Oh, there was a question or rather problem for not able to run, sir, as window it is going below taskbar. Oh, that is strange. So maybe what you can do is you can lock your taskbar. Can you try locking your taskbar? Okay, thanks. I think you have done it. Fine. Hopefully it is kind of end. So how much it has done? Let's see. 70% is done. Let's see how much it has done over here. It is done. So you see that after it is done, it will lot of temporary files will be removed, and you would see this many files. And out of which one important file is this out file. You can just click here and check, and it will show you that what are the process it has done. And if there is any error, it will also throw you. and it will also tell how many iteration it has done. Basically all the things whatever it has done and what it could achieve and all are there, right? So if you go back here, and you should see that your solution is done, run is done, and it will be indicated by these two green item. That is, one is this tick mark and then another is your flag. You can double click any of them, or you can also click here and say view now. So either of these three way is okay. So you can double click here, you can say view now, or you can double click here. So let's say I double click here, and you should see the shape created. From this side, it does not look much. If you see this over here, you should see the shape it has created, right? So you should see over here. So it has removed the material where it is not required, and it has created some shape. Now, the reason it has created shape in a free manner without following any guidelines of any manufacturing process is because we have not given one, right? If you would give, there is option that you can also give some manufacturing constraints such as 3D printing. So I can, for that purpose, what I can do is, which I'll not run, but I'll just show you how you can make it a shape which would be suitable for a specific kind of manufacturing process. Here it has done just random removal of material without following any manufacturing process, guidelines. Now to come back or rerun this optimization study for another set of say constraint, you can go either from this radio button. So right now this radio button is selected, which is the optimized shape. I can either go from here or I can go to switch to design space. Either of which is okay. So if I go back here, it will bring me this one. You just close this shape explorer. Now you get back your design space, and you can also go to your shape as well. I mean, optimized shape as well anytime. Now, if I want to do another iteration, all I have to do is with the shape control, all I have to do is I have to go to the shape control. Again, there are two icons. One is for symmetry control, another is for shape draw direction. So these two are part of your shape control. So I want this draw direction. Click here, and I can choose this. And there are many types of shape controls available. Draw directions available. First one and second one are for casting and forging kind of design. So I can say that I can choose the parting plane of certain way, and then it can generate the shape accordingly. So I can, if I want to make it casting, then I can make a parting plane like this, so a draft angle will be maintained. Similarly, if I go for say extrusion, it will create something like machining kind of design where there will be no, draft angle. Whereas if I go to shape control over here, you will see that there will be draft angle of the split draw and single draw as well, right? Then there could be radial shape control where you can make a kind of circular kind of design, right? And the last one is what is called overhang constraint. Probably we'll make it like this. In overhang constraint, what it does is it is related to 3D printing process, which allows to create the design in such a way that your support requirement will be least, right? So your requirement of support will be least, right? So you can choose the printing direction. I can say that this is my printing direction, and I want to create some structure of my optimized design in such a way that when if I print it in this direction, I would require least amount of support, right? So like that also you can do. However, we are not doing it today, but I would request you to, or rather invite you to, try that as well. So we got this shape now. I hope many of you have got this shape of optimized shape. Now, next step is to understand whether this shape or this geometry is strong enough to hold this load. So if you remember our target, or rather, objective function, and the target was to achieve 30% of the existing design or existing design space. But that 30% is enough or not, that we don't know. We know that we have selected the best possible 30% where it contributes the maximum. But then 30% itself may not be sufficient to withstand this load. In such case, you would see a higher stress and displacement, right? So that kind of confirmation, especially when you are into minimize stiffness kind of objective function. If you go to minimize mass, here you are actually giving a factor of safety target, right? So both the way are there, but since we have done a minimized stiffness over here, we have to we have to do a secondary confirmation that this 30% whatever we have removed is sufficient, or we are not creating large stress or displacement in some areas beyond acceptable limit. How to check that? Again, it is very easy. All you have to do is you have to go to my this shape show optimize result icon. So this option, go over here and it will bring this slider. First thing what we'll do is we'll put this slider little bit two step on the right hand side. What it will do is it will add some more material. Why I have adding some more material is because if you see that some of the area these connections are not very proper with the 30% target. So that means that 30% may be giving you a shape, but all the areas are not well connected, or if it is connected, it is very narrowly connected. So that's why I'm just sliding it two step up so that I get some more material. Since still there are a lot, I mean, it has optimized a lot. So maybe it is going instead of 30%, it is making 35% or something like that. And after I do that, what I'll do is I'll go to analyze. I'll click analyze. And what it will do is it will take this shape wherever you put your slider. It can be 30% or maybe little more, that is 35% or so. And then it will run the analysis. It will run the analysis with the load and support condition, whatever you have already specified for your optimization. So whatever you have already specified for optimization, it will take that load and it will run the analysis. And now the purpose of this is that you want to understand whether your stress and displacement are within limit or not, right? Again, it will run. It may take few more minutes, so we'll not spend time now. I'll show you the result probably. So if I go over here, yeah, over here. So if I go over here, you will see the result like this, right? You will see the result and of the FEA. And in that FEA result, what you will understand is your stress and displacement, and which is very critical. You will see that it is giving a max stress of 21 MPa, and you have displacement as well, and you can play animation as well to understand how the things are behaving and so on. So this will give you the idea that whether your optimized shape is having the targeted accepted the values of your stress and displacement or not. So that thing we are confirming. So let's assume that it is confirmed, we are okay with this stress and displacement level. Then we can go to the next stage, that is generating the design out of it. So these things are, although it looks like a CAD, but you remember these things are kind of mesh. So you cannot really do many CAD operation on this kind of geometry or optimized thing, right? You have to convert it to a CAD. How to convert it to CAD? So to do that, what you have to do is you have to go to what is called polynomial, this step. And in this, what you will do, you will go to fit. You'll go to fit, and then you will choose with your left mouse button with a box selection. You will choose the complete, this body, all these things, that is your part as well as optimized shape and all, and then you say play, this play button, hit this play button. So what it will do is it will convert that design optimized geometry, which is shown in the brown color, to actually watertight CAD, which is like you can use it for any purpose, right, including 3D printing and all. So that's what it is trying to do, and then it will automatically it will do. Of course, there is a manual option as well available, but you can use this automatic option, which is much easier, and everything is taken care by the tool itself. You don't have to spend, or you don't have to do anything actually, to be honest, right? So let me take some water. Any questions so far? Anybody? Please drop it in your chat box if you have any question so far. Okay, fine. So now you have to right click and come out of the of your command of that fit, so that it will give you this geometry. It may take a couple of like maybe 1 minute or so. So after that it will come out. So you'll see that it has created the CAD out of that, you know, model, right? So now once this CAD is created, next step remaining is to you have done two things now. One is you have optimized, and then you have also validated that my optimized shape is structurally performing well. All those limits are meeting. Now next is your process simulation. So that means whether this thing is printable, and if it is printable, then you know what are the kind of oops, what happened? Am I audible? Can you confirm? Because momentarily I saw this zoom control was missing.
Yes, yes, sir. You're audible.
You're audible,
Oh,
sir.
okay, thanks. Yeah. So we have done that two-step, that is optimization, and we have also ensured that my structurally this part is making sense, right? Now next thing remaining is to validate it for my process. And to do process validation, what we'll do is we'll save this file and save it in Parasolid, right? I have also given you actually the saved Parasolid file. You can also use that. But if you want to save it somehow, you can do it with Parasolid, or you can also save it in STL as well. If you directly want to print and send it to your printer and all, so that also can be done. But it is preferred that you go with the Parasolid route because that is a CAD. And I think I have saved it in this 3 spinal for print, this part. So you can save it in similar names, or you can use my file as well. I think we are on this. FEA is done, polynobs is done, and we are saving it over. So we are over here, right? Then we'll do for next stage, that is our 3D printing process simulation. Again, in the same tool only it will happen. So all I have to do is so my analysis is also done. We have already seen the result anyway, but we can also see over here as well. This is how you will see. So now we'll go to print 3D. So print 3D is essentially the way we'll do process simulation. We'll go to this tab, and we'll not use this mesh and all those complicated things. We'll directly start with our saved model. So we'll go and say file new model, and we'll say don't save now. So it will clean everything, and we'll say Control O, and you choose that for print underscore x dot x underscore b, that model. You just choose that, you know, so that it will start afresh. So it should load that. So you'll see that this file will be loaded. This may look a little different because I think I have done it in previous iteration. My setting was a little different, but this is the workflow. So once that is saved, only thing you have to take care about is this icon over here. So you'll see that there is a cube. There is a cube, right? So that is important. Make sure this is cube and this is not a plane, because if it is a plane, then there could be issue. So make sure it is solid, right? So once you are ensured that, you will start, you go to print 3D tab from structure. So here in structure, we'll go to print 3D. And first step, what we'll do is we'll choose the print part. So we'll select a click here. Again, there will be multiple icons. Make sure you select this area, which is called print part. So you select that and choose this part. As soon as it will choose, there is a instruction as well, small icon showing what is each command and all. Or you can again go to F1 as well. By pressing F1, it will take you to help. So now print part, and it will give you an option to go for material. So you have to choose the material for 3D printing process simulation. So we are going ahead with titanium, but you have other choice as well. And if the part has a lattice structure, make sure you switch this on, because then the way the meshing treatment will be given will be different. But here we don't have a lattice. We'll see on example on lattice as well, not for printing, but creating how to create lattice, but later on. So this material part is done, and then you can right click and come out of this window. So you'll see that your color will change, and make sure you see that it has been identified as a part. You can close this browser and property editor to get some more space here. Next is your printer. Now in that printer, there are multiple standard printers available with its own model and all. However, if you don't have that printer, you can just create default printer, which will take care about your component size and it will create the printer. So you see that it has created printer. There are two things. One is it will show you the ricotta direction and your printing direction, right? So that is your printer. Next is your orientation. So what is orientation? Orientation is essentially telling that how you are going to orient the part in your print. Now, there is an option or there is a possibility to optimize your orientation to make sure you do optimization between two things. One is your support requirement and your printing time, and the third thing is your distortion, right? So those things you can take into consideration before choosing a orientation. So if you see for this particular orientation, if I hit save, you see that it is telling me that I need a support area of say this much millimeter square, and you will see that support areas. So you'll see that these yellow areas are actually support required, right? And it will also tell you the amount of time required for printing. Now if you see the other orientation, say I want to orient it on some say other surface. So I say this orientation with respect to this surface. You see that it has oriented. So now you see that it has oriented in other orientation, and you see that your values will change, right? So you can anytime go and change between those orientation as well. So if I say this orientation or maybe that orientation, it is changeable, right? You can do that. So there are different ways you can orient it and you can understand. So there are ways options, say minimum height, minimum build height, maximum build height, then all those options are available, and you also have another option of orient optimization where you can tell that, or you can choose a right kind of orientation for some other parameters as well, such as say distortion or printing time and so on. So it will give you this kind of contour where it has three parameters. One is time required, support, and your deformation. So if you choose the green areas, so that is what is favorable on each of those parameters. So for example, I want least amount of time. However, if you see that in this case, your support and deformation may not be the least, right? Maybe I'll go to support over here, right? I'll go to support, and it will then, you see that it has moved here, right? Now my time and support both are in my support is in favorable condition, but my printing time is increasing, right? And so on. So you have to choose the, or you have to do the trade-off rather, you have to do the trade-off. So if I probably, this is the trade-off, I mean best trade-off possible, right? And then you can stop here. So there are many ways it will give you to orient or choose the orientation in your how you want to do trade-off, right? So once whatever way you want to oriented, you go to support then. So it will create the support automatically. Of course, you can bring your own support as well. So if you have created support elsewhere, that also can be brought. So there is another tool over here. If you see that, manual support, and you can also bring, designate support option is also there here. So that means you have part model different, support model is different, and you want to designate them. So that also is possible. But here, let's say that we are creating manual support, right? And now, automatic support. Now this support is created. This is solid support, this type of support, but you can also change the type of support. I can say that I want a perforated support. And for each of those type of support, you have different parameters to play with, and you say create those support. You say that there are different types of support created. Similarly, you can make tree support and so on. So there are many possibilities as far as the support creation is concerned. You can make additional manual support as well. You can go to manual support and put some extra support as well. So that those options are also available, right? So once that is done, support is done, you can again come back, come out of this command. And then you can go to slice. So slice is basically not compulsory, but it will just give you a overview that how those each of the slice will look like and where you have which section is getting sliced. Again, this is not compulsory to see. Then you can go to export this. You can say, because you want to print it through some machine, you can export it, and you can export the part and support in a different STL and send it to machine. And again, not compulsory over here. And then finally, you want to do the process simulation, you go and click in this run 3D print analysis. And here you have this dialog box. Again, it will, like our optimization and FE analysis, it will give you option to run, give a name. There are analysis type. We prefer, we recommend that you go with thermomechanical instead of just pure thermal. And then scan strategy, it is always layer. And then you have some more parameters such as your velocity, laser power, then your powder absorption percentage, then your cooling time, that is end cooling time, then your bed temperature, that is base plate temperature, and then your element control, right? How much size you want to have element. And then you have a simulation speed versus accuracy slider. So you can say it is fast versus accurate, so that you can play with. So when you are want a very accurate result, or rather result is to be compared with something, then you go ahead with accurate. If you are into the initial stage, just want to see the behavior, you can just go for fast. Irrespective of fast and accurate printing, the simulation will take a little longer time, maybe 15-20 minutes. So we'll not spend time over here. What I'll do is I'll just show you the result over here. So you should see results something like this. So there will be this kind of result, that is displacement, your 1/c stress, and temperature. So these are three types of result what will be important for you. And okay, let me just play the animation so that you understand. So it will start from your 0. So you'll see that it will start printing. In this case, what the result I'm showing, I have printed in vertical direction, but you can make it other way around as well. So if you observe over here, there are many things happened in between while I was talking. So it will print layer by layer. So it will show that each layer, how it is getting printed and what are the values of each of those result type. And at the end of that, what will happen is after the printing is done, what it will do is it will cool down. So if I put a call out over here, you'll understand. So let's make it say temperature. You will see that it will cool down. So you'll see that right now it is 190°. Oops, not displacement. Let me make it temperature. You see that, or make it mm. So you see that this is 927 degrees centigrade. Now you'll see that it will start cooling down. Okay, so 970 was not the maximum. Maximum was something else. So you'll see that this 560, yeah, 970, then 338, then 240, and then 126, right? So that's what is happening. So it will cool down, and after the cooling is done, what it will do is it will remove the support. So there are three things happening: printing, then intermittent cooling between the layer, and then after the printing is done, it will go for end cooling. And then finally what it will do is it will remove the support. And during this complete journey, there will be result variation. So for example, if you see that, if you go here, you see that temperature will gradually decrease, and then there will be support removal, and again further it will remove, decrease. If I go to say displacement over here, it will have different behavior. Displacement will start increasing because you will remove the support, right? You will remove the support, and suddenly there will be jerk, huge displacement, right? So those things are very important because that will help you to decide which orientation is better and which optimized shape is better. And accordingly, we'll select your component, and then finally you choose your optimized shape as well as your process parameter, which will give you the best of both world, that is structural world as well as manufacturing process world. So any question on this so far, anybody? Let me see if there is anybody on the chat. I don't know why the chat is not coming up. There is chat. Okay. Why don't we put the object on the surface directly? Is there any reason? Okay, so there is a question from Mayur. Why we cannot put directly on the surface? The reason industry don't do that normally is that because you have to remove this support, and removing of the support will require a machine, operation, right? If you put directly this part with the base plate, it will be firmly attached to that base plate, and while removing it will be difficult. So you may actually have to do machining of your base plate itself to remove, or some wire cutting, and that will in turn may reduce your quality of the base plate itself. So that's why there is a standard practice that you choose put certain distance so that your support is created a little bit, and these supports are weakly created so that you can remove it easily, right? So that is the reason. Any other question? Anybody else? Anybody? Anything else? Okay, so there seems like no question. So if no question, then what we'll do is we'll go to the next topic. Not next topic, related topic rather, where we'll see how to use this platform Inspire to create lattice. So like we did optimization to generate our design, similar way, many, especially the medical application, don't go directly for optimization. They prefer creating lattice structure in the desired area. So, and then they do further things such as maybe do structural analysis and then go for process simulation, that is 3D printing and so on. So if that is the case, then in such situation also Inspire can be helpful. So how to do that? Very simple. We'll start again with our, say, clean this model, and then we'll again start our first design, that is 00. This model, we'll bring this model again. And now once I bring this model, what you have to do is you have to go to polymesh. We'll go to polymesh. Initially we are on structure, then we are on print 3D for printing, 3D printing process simulation. Next we'll go to polymesh tab. In this polymesh, aim over here is to convert this design space, which was earlier design space, to lattice. So how to do that? Very simple. All you have to do is, again, left to right, you have to choose this fill option, and we have to select the area what I want to convert. And as soon as you select, it will convert this shape. And there are different types of unit cell available, and those are parametric. So I can actually play with make it small, big, and so on. Or I can even make it say that unit cell itself can be rotated, so that unit cell, I don't know whether you have observed it or not, this unit, each of the unit cell can be rotated, right? That is one. And I can also change the type of unit cell itself. So right now what I have a BCC, I can make it like SC, or say SCBCC, or face FCC, or say trace and truss, or say diamond cube. So all those types of unit cells are supported, and your design will change. And all these are parametric, so you can change these values and it will change the all those things. For example, in the beam radius, instead of 0.25 mm, if I make it 0.2 mm, you will see that there will be change, right? You'll see that there will be change. So you'll see that that has changed, right? So likewise, this way you will create this mesh, and after this is done, you will just say close. So your mesh, or rather lattice, will be created. However, if you want STL of this file, you can directly file and save as. You can say file save as, and it will choose STL as a format, and it can directly save this and this as a STL, and you can go to printer and then fire the run. However, if you want to make a CAD out of it, then what you have to do is you have to do what is called convert. So you can choose this lattice part, and you can say convert, and what it will do is it will instead of mesh, it will create a CAD. CAD is like, as you know, it is watertight CAD, and then all those CAD kind of operations are possible. However, in 3D printing world, you may actually stop with STL itself. Um, that's absolutely fine, and you can save from there as STL. If you want to have a CAD, then this process will help you, and then you can do save as, and then it will help you to save it in Parasolid or Step or IGS and all those CAD file format. However, this process is a little bit of time extensive, because each of those STL or each of those lattice has to be converted, and there are algorithms for that. And this will be heavier as well, because there are a lot many surfaces as well. STL will be much more lightweight, right? So that is the overall process, how you can do what is called lattice generation for your design, right? So this is the process what I have said. So with this, I kind of would like to end this demo part, or rather training part, and I'll come back to the I'll go back to my what is called presentation. But before that, in case if anybody has any question, okay, the lattice structure penetrating the inner wall, can that be controlled? Yes, it can be controlled. So what you have to do is, in such case, or normally people what they do is, since I am using this, it is already hanged. So let me show it on another model. So what you have to do is you have to play with those parameters. So basically, if you go over here, you have to give a thicker this wall. So you have to make this wall thicker. So if I go hide, and if I go to geometry, if I go here, and let's say 5, right? So basically, you have to make sure this guy kind of thicken up, or it is not thickening up. So while modeling this, you have to make it thicker, and then that will give that lattice to have enough space to be within this boundary, right? So it is very thin, that's why lattice is coming up. So if you make it thick, so that lattice will not cross. That is number one. Number two is, if you don't want to do that, then you can also play with the parameters of the lattice and make sure that those length and all does not that diameter of the lattice is smaller with the order of this. So it is essentially the diameter which will cross. So if you make that radius of that lattice in this order, the thickness of this, so it will not cross. So there are two ways you can do that. Another way people do is that after they convert it into CAD, they actually boolean it. So actually they chop those extra lattice, and then they delete those things. So that can also be done. What is the cooling time to remove the finished object which is completed? Okay, so that you cannot control today. So that is algorithm dependent, and it is fixed. So you have that in your setting. So that means for, okay, so if I go back, if I go over here, so there is something called cooling time over here. So that is, I mean, that is a single value for complete cooling. So that is what 150 seconds over here. So after you fire the run, you cannot control it. So before firing run, you have to set it over here. I hope that makes sense. Does it make sense, Niranjan Babu? Okay, thanks. Okay, so now I'll go back to my presentation. Since we have around say 30 minutes left, I think that would be sufficient for me to put some, share some learning of DFAM. This is already done. So the learning of DFAM is what are the good way of doing DFAM, so that you are benefited. So based on the projects, whatever we have done so far, these are learning what we have. However, I mean, It can be further enriched, or it can be, some of the things are subjective in nature, so it can be actually what I could say argued as well some of the places, but this is our finding, and we feel this is kind of best practice of a DFAM project workflow. There are 7 steps. First one, and very, very important one, is part screening, right? Second is optimization. We already seen that. Part screening we have not seen, but that is very, very important to make sure that you select the part which has a potential, or which has the benefit, which goes hand in hand with the advantage of 3D printing, right? So you should screen that. Then you have optimization. Then you have design rules. There are many design rules, right? While after optimization, how you make it like detailed design, right? There are many things which will govern, such as your say optimized part will give you a very high level overview that where you should remove material. But after that, you have to do some detailing. Say you have certain holes. That holes can, if you print it in certain direction, it can become oblong and so on. So those rules are you have to implement while you are in between optimization and detailed design. Then you will get to your detailed CAD. After you have a detailed CAD following the optimization, part screening, and your design rules, thumb rules, you have to do structural analysis to ensure that your detailed design is not going to fail in the structural condition or your external loading condition. Then you will do for orientation optimization. Now, and then you will do for print simulation. However, these steps I have listed linearly. However, this may not be the case, right? So you may also have learning in different stages. Say in FEA, you learn that your structure is getting failed, or in FEA, you understood your design is showing over design. That means your permissible stress is 250, you are getting say 900, or your permissible displacement is 1 mm, you are getting 10 mm. So in that situation, your target of optimization that you have chosen 30% or 40% may be actually revisited, right? And so on. Or it can be other way around also. Your stress target is 250, you are getting 150. So your target of optimization may be, relaxed a bit. So all those things you can come back here. Similarly, when you are into orientation optimization study, you may actually get a different orientation than what you orientation constraint you have given. If you remember, we have orientation constraint, or rather 3D printing constraint available during optimization. And after giving that optimization for optimization study in the optimization stage, when you actually came to the orientation optimization simulation in your print 3D, you saw that there might be other possible, better orientation available. In such case, you can go back to your optimization and retune your orientation direction, or that overhang direction, overhang constraint, and do that process again and again, come back here, right? And then in the printing simulation also, you can get this input, that in the printing simulation, you see that certain orientation, which you earlier thought was best, may be giving some surprise in terms of distortion, right? Or maybe, residual stress. And sudden other, you want to see what would happen if I change the orientation. So you can again go back to your orientation. So the idea I'm bringing over here, it is DFAM is more, is both that science as well as art. It is not like FE, just you press one button and you get the result and you say this is good or bad. No, that is not the case. There are a lot of subjectivity, lot of experience involved, and that's how this is little specialized job, right? Now, coming to the first step, that is part screening. There are many ways you can do, and there are many questions you can ask to select the right part. So for example, if you have these two components, these two are actually same component or design of the same component, which have same application. It may not look like that, but this is the case actually. So if you see that this pivot and this pivot is the same. So this is basically holding this, and the purpose of this to hold a, actuator, that means cylinder, and this, all this, and this, these are actually mounting hole. So although this does not look like same, but these are actually same part, right? Now, if you want to understand whether which component I should choose for 3D printing, or rather the chosen component or chosen design is really require 3D printing or not, or is it better if I go with conventional manufacturing process? So that is a very good you know um, very good initial study before you go for optimization. And there are many thumb rules over there. So for example, you can ask a question such as whether my design chamber is sufficient enough, what is my ALD volume and all. There is actually a calculator which I created in my blog, as you know, probably from my previous introduction, that I keep writing a blog. So if I go over here, so I think let me paste this. If in case you are interested, you can go here. I don't know how to paste it. Yeah, I think I can paste it here. So you can go here, and there would be a calculator. So let me open it up as well. I think it's already open. So there is the calculator. This is not my work, to be honest. So this I have. There is a gentleman named Zuran W. Bruth. I think he's from France. He did a PhD on this selection procedure itself, and he kind of came out with his thesis and he published it online. And then with his permission, I kind of made it more friendly for the people who don't want to go by literature. So here what it is telling is essentially there is a DFAM scorecard. And okay, let me, what I'll do is I'll make it side by side so that it will be more meaningful. So there is a DFAM scorecard. What it does is, okay, so what it does is it help you to select part actually. So how? So let's do this for both this component. And at the end of the end of this going to scorecard, it will give you a score, and based on that, it will actually, you can actually tell that whether the selected part is good for DFAM or it is good for conventional manufacturing process. So let's start with this part first, the left hand side, right? You have to answer some question actually. So if you see that first one is complexity. So you have to choose one. So the part is same shape as common stock material or is completely 2D, or part is very curvy. So this question is related to how bionic the component is. Is the part like regular shape where you can actually make it by normal machining or those kind of thing, or there is a lot more curves and bionic in nature, which will be very difficult to manufacture by say casting or forging or say machining and so on. If it goes, it will take lot much time to do, come out with the tool and so on. So if you see in this part, this is more or less a very simplified part, right? It is more kind of 2.5D kind of part. So it may not be 2D, but it may be actually 2.5D. So the part is made of mill lathe. That is what it should be. So I'll choose this one. Second is the functionality. So matting surface or bearing surface. So what happens is for 3D printing, the components which are connected with the system which are connected to the 3D printing part. As you know, 3D printing part does not produce a very highly accurate surface. You have to do some post operation if you want to do that. So if your component have lesser of such kind of surfaces, it is more better. I mean, it will have least cost in 3D printing. So this is what it is telling. AM parts are light and medium duty. So that means you cannot have very strong fatigue operations, those kind of components, which is say engine mounting brackets and those kind of thing, may not be good example in such finding. And again, this finding is for that gentleman. So what it is asking is that matting surface or bearing surface are expected to endure for 1000+ cycles. So that means it has a fatigue requirement more than 1000 cycle. It has a fatigue requirement of 100 to 1000 cycle. It has a fatigue requirement of 10 to 100 cycle, and it has very less fatigue requirement, and surface are stationary. So if it is a surface are stationary or part is stationary, that is actually ideal for 3D printing. But for this component, there is a actuator. So there is some requirement actually. So I'll choose this one, and this will remain true for both the component actually, both the cases. Now, third option is material removal. So support structure ruins surface finish. So if I manufacture this component by 3D printing, how much support required? The least the support required, the best it is for 3D printing. So what it is telling, that part is smaller than or the same size as the required support structure. So that means support proportion itself will be much higher than the part. If that is the case, or there are no support required. So what is the extreme? So in this case, I see there would be requirement of support, although it will not be like it is more than part itself. I don't think so. So maybe I'll make it like this. So there are small gaps, there will require some support, right? Then does it have unsupported feature? So that means if I don't put support, will the part be manufactured? I don't think that is the case over here. You do need support. So there are long unsupported feature, there are short unsupported feature, there are overhang feature which have sloped support. So there are short unsupported features. So I'll choose this one. Now thin feature. So as you know, in 3D printing, you cannot create very thin feature. So does this part has very thin feature? So I think yes, there are some feature which are like 1.5 or 1 mm, right? So maybe I'll make sure that walls are between 1.5 to 3 mm. Then you have stress concentration. So is there a sharp areas where there can be chance of stress concentration? In this part, yes, there are some areas. So I'll say there are some areas which have interior corners have chamfers, fillet, and ribs. Interior corners have no chamfer, fillet, or rib. Interior corners are generous chamfer and fillet and rib. So there, I think there are very less chamfer and fillet. So that's why I'll choose this one. Tolerance. So again, for 3D printing, tight tolerance production is not possible. So hole or length dimension are nominal. Hole or length dimensional length tolerances are adjusted, and hole or length tolerances are considered are not important. So basically, tolerance is how important for this component. I think it is medium. You need some tolerant, I mean, tight tolerance component over here, tight tolerance hole over here to function. Geometric exactness. The part has large flat surface or has form that is important to be exact. So basically, if you have very long surface, which is to be 3D printed and which has to be exact, that can be challenging in 3D printing, right? So in this case, you have, I would say it is medium, right? So our score is say 28. So in this case, our score is 28. Now let me open another of this tab, and maybe I'll open this for another for this part as well. So it is saying 28. Now what this 28 mean is that if your score is between 24 to 32, you should consider redesign this part for AM. So this part is not as is suitable for AM as per this scorecard. Now let's see this component. So we'll go back here, and again we'll answer this question. Complexity. The part has same shape of stock material. No, this is quite complex geometry, right? So there are interior features, surface curvature is too complex to be machined. So that is why this option is true for this component. Functionality, I think this will remain same like what we did in the previous case, but because functionality will not change, so we'll choose the third option for both the cases. So I'll choose this third option. Then material removal. So now in this case, this is bionic in nature and it will require lesser support. So there are the part is smaller. So I would not say there are no internal cavities. There may need some support, but maybe I'll say that material can be easily removed. So it is more of a support friendly than this one, right? Unsupported feature, there are not very long unsupported feature is not there. So overhang features have a minimum 45-degree support. Overhang features has a slope support. So it is not like 45-degree, but it has some slope, right? It is not like flat. It has not perpendicular kind of thing. So walls are more than 3 mm thick because the design has changed now. And stress concentration is not there. So it has generous fillet and chamfers. And tolerances, again, this is hole or length tolerance adjusted or shrinkage fit. So I'll choose the same option like this. Tolerances will make it same. So tolerances will make the second option. Tolerances will make second option. Then geometric exactness, again, I'll keep it same because the functionality is same. So part has medium sized flat surface or form that are should be choose to be exact. That part has small or no flat surface. So I'll choose probably this one because now the design has changed. And you see that now my score has become 15. So it's actually less, right? So if it is 15, so actually it is actually good or better. Maybe somewhat it is in the borderline. So it is actually suitable for AM. So this is one way to easily when you are confused whether this design is really good design or you should do some modification on your design, or that design itself is not at all fit for additive, this tool may be useful for you. Again, this is not a sacrosanct. This is, I just found this tool, but you can use your own judgment on those points and then you can take your decision as well. There are other consideration as well. For example, you should consider your machine, what you have, and accordingly you have to strategize your joining strategy of the component. If you are having small machine, if your part is big, you make sure it is printed separately and then welded, and that welding location should be not be in the critical area where the loads will come and so on. Then yearly volume, this is a very, very important aspect. Like if your part is having 5,000 kg per year per design, that is kind of normal rule. Then it is less than that, it is probably suitable for your 3D printing. Choice of material. For example, we took our spinal implant, that has to be titanium because without that you cannot, most of the biomedical application where the part is going to be sitting inside your body, you should choose a material which is your body will accept more easily. Also, you have to choose material which is which has good strength but less density, right? So those kind of consideration you have to take care. Does the current part have enough tooling cost? So if it is a very high tooling cost, it will be more favorable for your 3D printing. Does the current part have long lead time? Is there a desire or need for lightweighting? Is there an opportunity for consolidation, part consolidation? Is there an opportunity for mass customization or individual customization, such as I say spinal implant or dental implant and so on, right? Then you will go for optimization. You already know what is optimization, right? So basically you will understand the load, identify the load, supply that load to your software, Inspire, and then it will give you the shape based on your manufacturing requirement. And each of the manufacturing process can generate different kind of design. And at the end, you will get a different kind of design. In optimization, getting the targeting for least amount of support and targeting for strength can be two different things. So you have to do a trade-off, right? Sometimes that can contradict each other. So basically, if you can get a shape which will generate, which will require less support, but that is not optimized. So for example, if you see this here, this pre-design, it is much more optimized. However, it will require more support. On the other hand side, if you see this one, this is not so optimized, but it will give it will require lesser support. So you have to do a trade-off. There is another kind of optimization you have seen, lattice. In lattice also, there are two kind of optimization permissible within Inspire. We have shown just one type where I have selected the area and it will completely convert to lattice. However, there can also be possibility that you can convert partly lattice based on your loading. So that has been shown on the left-hand side, right? Again, as I said, minimum mass and minimum support are, there is a trade-off and you have to choose those options. So for example, if you see that there is a right-hand side, which is require minimum support, but it is much less optimized, right? When you are going for material validation, you also can take help from the Inspire to understand if you change from material from say steel to aluminum, what is the impact of it on the other things such as your mass, your stress, as well as your displacement. So for example, if you see that single bracket over here, it has in steel, it is close to 800 gram. If you go to aluminum, it goes to 212 grams. And more or less similar stress and displacement target it has, right? So those kind of study, you can also take help from Inspire by changing material, what is the impact it is bringing on your table, right? Now, this design rules, are quite extensive, and that is no one size fit for all the manufacturing process. All the manufacturing in the sense that all the 3D printing manufacturing process has, each of them has their different rules, right? So for example, if you go to powder wet fusion, that is LPBF, has a different rule than say binder jetting. The reason being that binder jetting has a additional step where, or rather many steps which are different, where you start with binder, then you go to a oven where you cure it, and during that process there is a change of mass properties of the component, and which can prone it to fall and break. So those are different requirement it has, right? And for binder jetting, maybe your consideration for lower COG will be more important than lesser support requirement. So similarly, there are, each of those process has their own uh, thumb rules. Follow the machine manufacturer guideline. Each of them publish their own thumb rules. So follow that and you will understand which is good and which is not good. However, if you want to generalize, there are some rules available. For example, supported wall, unsupported wall, what should be your minimum thickness? What should be the gap between the features? How the wall, or what are the holes, minimum hole you should can print? What is the minimum draft you can print, and so on for each of those process. And there are enough resource available in the net. One among them could be this 3D Hub. There is a good resource website you can visit. Choosing the right technology. Now, each of the technology of the 3D printing itself has its own pro and con, right? So for example, if you see PBF and binder jetting versus DED versus MME, each of them has their own, pros and cons. So for example, if you see PBF, powder wet fusion, it requires support. Whether if you go to binder jetting and direct energy deposition, it don't require support. On the other hand side, if you go to printing cost, PBF is high. If you go to binder jetting and say, direct energy deposition, those are medium to low, right? If you go to say strength of the component, if you see that powder wet fusion gives best among them all, right? Whereas if you see the surface finish, you see that binder jetting is much better. So you have to take a call based on the requirement you have, and based on the, all those metrics you have to consider and choose the correct technology. And that is, and accordingly your design rule also will change. Now, while CAD detailing by considering the optimized shape and the design rule, you have to consider many things, such as your um, uh, printer size, then your orientation, then your costing. So um, although these tools will give you some pointer to come to the detailed design, however manual fine tuning and manual experience is there is no substitute for that, right? So you see those the different examples over here where those minimum support. So if you see on the right hand side, top right hand side, there is a component which is printed where no support is required. And on the bottom hand side, you have made a design such that your CG becomes lowest. You see that it has redesigned, and that CG become lower in a sense that it will be much more suitable for binder sintering, right? Now, design for no support or minimal support has its own advantage and disadvantage. Obvious advantage is, as I said, the material cost for 3D printing, especially for this powder metal fusion, has its own cost, right? And as you keep it low, it will be definitely useful. But then there are also trade-offs, like you cannot always target for the lower, lowest amount of material possible, because then that time you may actually end up doing something else on the other side, such as your optimization weight may go up and so on, right? So in design for minimum mass, you understood that in optimization there are two ways of your design, right? Optimization, you can go for minimize stiffness or minimize mass. If you design for minimize mass, still you have to follow the design rules, and you have to make sure that your orientation are correct when you go for the orientation optimization, right? Now, in case of SLM, there are overhang is a big constraints or big, I mean, overhang or support requirement is there. So you have to make sure that overhang constraint is used properly. And in case of DED or WAM, so here you have welding machines and which kind of make those component, you have thickness requirement is much higher. So that means minimum thickness it can print is much higher, and minimum cross section is also much higher, and the kind of surface finish it achieves is much inferior than your LPBF and other kind of process. In binder jet, as we have already discussed that there are different steps. First step, you put the jetting, that means your glue, and then you create the green part. Then you take it to remove the powder and take that green part to your oven. You make it brown part. And then when the brown part, when you go for green part to brown part, you have it gets shrunk 20%, right? So during this process, there is a high chance that it can collapse and it can distort. And you also have to make sure that after this shrunk only, you should get your final component. So you have to redesign, design your part itself in the beginning in such a way that after this shrinkage has been considered, your part is useful for your final production. So this is what has been shown over here in the right hand side for binder jetting, right? Again, in such case, your G or the COG requirement is important. I'll finish it up. Maybe these are
Okay, sir.
yeah. Again, COG requirement, COG optimization also you can take benefit of. Orientation optimization we have already seen, and again this tool can help you. And these tools again, these tools are may not be 100% give quantifiable answer, but these tools are very good in terms of getting the judgment and saving lot of time and cost of your machine. Otherwise, you have to run it every time, right? So I'll end it over here, and probably I had one case study, but maybe we'll stop it over here, and maybe if you have any further question, we'll take because of the time. So if you have any question, please do let me know. Let me see if there is any question.
Any questions from the audience? Please, you can ask questions.
Where to create the model in Inspire, able to create any? Okay, yeah. So that is a good question. So here we should start. Where we should start the CAD. So normally, what happens in industry is that you don't start it from scratch. You already have a design, and you want to redesign it for DFAM. So in such situation, yes, you can just import the part, and then there is a capability within Inspire where you can modify it and convert it to design space. So that is possible. If you want to create a component from scratch, again, Inspire can help you. You go to sketch and geometry. There you can, create the part from scratch itself. So both the options are possible. I think I forgot to send this link of the calculator to everybody. So I'll probably send it here so that it goes. Okay.
You can send me the link, sir. I'll put in their WhatsApp group also.
Okay, sure, sir. I'll send it to you so that in any case anybody is interested,
yeah,
please. So bottom line is that please refer each of those manual of each of the manufacturer of machine, and they provide those detailed guidelines for each of the procedure, especially on the steps number 3 when you go for detailed design after optimization, right? And follow those rules. And of course, you will start with your CAD, you go for optimization, you create your detailed design, then you go for structural analysis, and then you finally go for 3D printing process simulation. As I said, that is not linear. You can have to iterate and reiterate. And the best part is that since this is a part of single tool, iteration and reiteration will be extremely easy. Okay. Okay, if no more question, then probably I would end. And Sorry for overstepping a little bit, maybe 3 minutes I have overstepped, but I hope the session was useful, and please do share your feedback. If not now, maybe offline. And in case, yeah,
participants will be giving, sir, now only as per the AACP. So we we have already shared the feedback link with them, sir, Google form. And
great. And in case you have any questions, any doubt about when you will go back to your tool, please do reach out to us.
yeah.
My name is Shibashish Ghosh, and you can reach out to me through sir as well, or maybe should I put my email ID here?
You can put, sir. I will also share with them. You can also share in the chat box.
Okay, so in case of any question, I can direct you to the concerned person if you have any issue, any times, anywhere. Okay. So I shared my email ID. So okay, then thanks all for attending this session, and take care. Bye.
Sir, wait, sir, please stay, sir, please. You can
Sure.
switch on your camera. So,
Okay.
any faculty, any participant, you have any questions, you can switch on your camera and ask the question. Or if no questions, anyone can give feedback on the session. Can say what is your experience of this session. Hello. I hope I am audible. Any participant want to give feedback on the session, or you have any questions, you can ask. Dr. Raghu Babu. Sir, am I audible, sir? There is a comment that super session. Sir, there is a question in the chat box, sir. Any new composition of any alloy can be added in the materials library? If so, how? Question is Balachandran, Professor Balachandran.
Oh, okay, sir. Yeah, sure, sir. There, if you go to your in the first step, when you let me just quickly share my screen so that I can show. So if I go over here in the first step of your, I hope my screen is visible, right?
Yeah, visible.
So if you go over here, so there is something called material viewer, and here you can actually customize, not only customize your material or add your material, you can also see what is there in the material properties which is being used for the simulation. So there are these 3 groups of material properties what has been used for the simulation. And in case you want to customize or add some more material, you can just import it in CSV format, or if you want to edit them, you can just edit and then give a name, say custom or whatever, and say save. And then okay, so there's already existed, so maybe I'll make it some other name, and you can save it. So these all values are then editable, and then not only that, you can even export it and give it to your friend, and then they can also use your material. So essentially this will be a XML file, and which will have all these properties. So make sure you know these properties, and many of them are actually temperature dependent, and you can customize or edit your material like that.
Thank you for responding, sir. To be more frank, sorry, I was not able to have your software installed because my machine is on 32-bit, and hope a few of us also had this issue. I was only a spectator all the way through your presentation. Thank you very much.
No problem, sir. Thank you.
Sir, Balachandran, sir, is the head of the department from Tamil Nadu, no, sir, college.
Yeah, I am the professor. I am a professor here at the School of Mechanical Engineering, Shastra Dean University.
Yeah, Shastra Dean University.
Okay, sure. Sure, sir.
Anyone wants to say anything with any questions, or you want to give feedback? Anyone? Kandaswamy, sir, you have anything to say?
So there are some questions in the chat box.
Okay, please.
So it is telling, can the same be done for small assembly model? Yes, you can do that. Like I have shown a presentation. In the presentation, there was a landing gear. So you can have multiple components and you can have assemblies, and you can do that as well. So then there is there OBJ file work here? Yes, you can import OBJ file as well. That file format is supported, to be honest, but I have not yet tested it. I mean, myself has not tested. So for example, if I go over here, there is a OBJ extension I could see, but I never used it actually. So if you go to OBJ, so you'll see that OBJ file is there. You may test it, but I have not tested it, to be honest. So that is one. Then what else? Does antivirus interfere with the running of software? It should not actually. In fact, I have antivirus in my machine, so it should not actually. I have Semantic, I guess. It should not. In case if it is, then we can work out. Let me know if it is creating problem. It should not actually, to be honest.
I think generally any official version will not have any problem with the antivirus.
Yeah.
If it is something pirated, you'll have the issues. So,
Yeah.
thank you, sir.
No problem.
Avast is creating trouble, it seems.
Oh, Avast is creating trouble, sir. Oh, Avast is creating trouble. That is good to know. Let me pass this feedback to my development team and let's see what is their feedback on it. Because I don't have Avast in my machine to confirm, but I'll.
Has the participant installed official version or trial version or any other one?
No, official version, sir.
Official
installed,
version.
But Avast software, is it antivirus software? Is it official one or is it
official, sir? Official from the official website. When I do topology optimization, when I click run, some text file the software tries to edit, sir. I don't remember the text file. So my virus says that the software is trying to modify the text file. So do you want to allow? So before I click allow, the topology optimization fails. Then I disabled Avast. Then I again ran topology optimization. Then it
yeah,
ran.
so maybe this is the, okay, so let me share my screen. So maybe this is what it is trying to access. So basically it creates a file and on your C drive. And this is a text file which it continuously write this information.
Yes, sir. Yes.
So maybe that is the reason. So maybe what I would suggest is maybe you can change the, so what you do is you go over here. You go over here and say in the file preferences and you run option, you switch this option called run in the model location.
Okay.
So what will happen is it will create those file in the D drive where you are saving the file instead of C. So sometimes C, it kind of, this software, those antivirus can have some problem in C, right? So that way you can check. And in case you still have problem, please do reach to me and we can have one-on-one private session to overcome your problem.
Yeah, sure, sir. Sure.
Okay, thank you.
Thank you, Dr. Sir.
Sri Krishna.
Sri Krishna, Doctor, sir. You are from Haseva. Thank you, sir. Sir, on behalf of the organizing committee, I would like to express my thanks to Mr. Shubhashish Ghosh, who has delivered such an excellent lecture on topology optimization, its importance, because topology optimization and additive manufacturing goes hands on. And because of additive manufacturing, what are the optimized topology you are able to print? And I think both of them plays very important role in developing new things, new type of concepts, ideas, etc. And I think you have given exhaustively hands-on practice. I hope most of the participants had a hands-on practice on the software. And this is a rare thing that on an online mode, you have a hands-on practice. I thank you, sir, for providing all the software, everything, the trial version you provided, and also the for exercise files. I think you have provided and also demo also 1 week before you conducted how to install everything. So thank you very much for your support from Altair. Definitely in future, we'll be conducting more programs and we'll require your support and we'll invite you. And thank you very much, sir, for your excellent presentation. There's a lot of feedback. We can see when your presentation is going, around 95 participants are there, sir. So it indicates the interest. And I think most of the comments you are getting is very excellent session, good session. It's a very good feedback. Thank you very much.
I would like to thanks you and all the team of Atal to arrange a session, and definitely this will help bridge the gap between industry and academia,
Correct.
and industry will be updated with the latest and greatest of the also academy will be updated with the latest and greatest.
Correct.
And my pleasure that you invited me, and I will be looking forward for such session in future. Thank you,
Thank
sir.
you very much. Thank you very much. Thank you.
Okay.